Are there any questions before I start?
Sir, in the homework, there's a question on rank, but it's not mentioned that R is an integral domain. So what do we do in that case?
Okay. So if there are no questions, let me begin. Okay. So last time we talked about localization of modules, and then we defined a rank. So we saw some basic properties of modules, like localizing product of two modules is same as first localizing each of the modules and then taking product, and localizing a submodule of a module uh, mm, uh, it makes it a submodule of the localized module. Yeah, and it behaves well with quotient. So S inverse of M mod n is same as S inverse M mod S inverse n, with this identification of S inverse n in S inverse M. Yeah, and and then we defined rank of a module over an integral domain. So if M is an R module over an integral domain R, then you localize this R module with respect to the multiplicative set consisting of non-zero elements of R. Then this S inverse M becomes an S inverse R module, but S inverse R is the fraction field of R. Yeah, so that means it's a K vector space where K is the fraction field. So the rank is defined to be the vector space dimension of S inverse M over K. Okay. So there is a equivalent way of defining it. So maybe I'll write it here. It's you can see it in the homework. So another way of defining rank is the rank of M is smaller. Rank of M is equal to the length of the largest linearly independent set. Subset. Or size of length, or maybe size is more appropriate. Size of the largest linearly independent subset of M. Okay, and you will see that these two are equivalent in the homework problem. So if you have a linearly independent set x1 to xn in M, then you can show that the rank of M is at least n. So if you can make the size bigger and bigger, then the rank grows. And conversely, if rank is some number n, then you can find finitely lengthen linearly independent subset in M. Okay. So that's the homework. Then we also talked about a little bit about torsion modules. So this was already defined. So set of torsion elements. So a torsion element in M is an element such that some non-zero element of the ring kills it. Yeah? So annihilator of little m contains a non-zero element. That's another way of thinking about it. Yeah. So M in M such that annihilator of M is not zero. Yeah, it's not the zero ideal. So that's another way of writing it. And we saw that if R is an integral domain, then the set of torsion elements is a submodule. So so you can say torsion submodule of M. Yeah, if R is an integral domain. But in general, the set need not be a submodule. And we say that M is called torsion free if the torsion part the set of torsion element is zero, consists of only zero. And so there is a okay. So we saw that if R is an integral domain and M an R module, then M mod Tm is torsion free, meaning it doesn't have any torsion element. So this we argued last time. And then last thing I mentioned was if R is an integral domain and M is an R module, such that every element in M is a torsion element, then rank of M is zero. So this condition means, maybe I should have written it as a definition, but this is such modules are called torsion modules. Okay. The point is, if M equals Tm, then rank of M is zero, and that is clear. So it's actually if and only if. So maybe I'll give an argument. So proof. So if M is, so maybe if M is M consists of only torsion elements, then we want to show that rank of M is zero. So so what we have to show is that S inverse M is the zero module. Yeah. So let alpha belongs to S inverse M. Then what does alpha look like? Is sum M over S for M in M and S in R minus zero. Yeah. But every element in M is torsion, so there exists, let's say, R in R not equal to zero, such that R times M is zero. Yeah. So that tells you that alpha, which is M over S, which is also equal to Rm over Rs, yeah, since R belongs to R minus zero, which is Rs in this case, yeah. So so M over S is same as Rm over S is same as zero over Rs, because Rm is zero in M, yeah, which is same as 0 over 1, which is the additive identity of S inverse. So we see that every element in S inverse M is the zero element. Hence S inverse M is zero, which implies rank of M is zero. Rank of M being the dimension of S inverse M as an S inverse R module. Yeah. And conversely, if rank of M is zero, then every element is torsion. So even converse holds. Yeah. So maybe I'll just write even converse holds. So if rank of M is zero, that tells you that S inverse M is zero, because rank M zero implies the this vector space must be zero. Yeah, otherwise the rank will be, if it is not zero, then the dimension is at least one. Yeah. But this precisely means that m over s equals 0 for all m in M and S in R minus 0. So you can take R to be is 0 over 1 in S inverse M. Yeah. So 0 in S inverse M, so to speak. But you can take S to be 1, for instance, which implies M over 1 equals 0 over 1 in S inverse M, which precisely means that there exists R in S such that R times M minus 0, so 1 times M equal minus 1 times 0, which is R is 0, which implies Rm is 0. Yeah. But R is in S, means R is where S is basically R minus 0. So this implies M belongs to Tm. So every element of M is in is a torsion element. Yeah. Okay, so this is true for all M in M. Any questions? Okay, so this is all we need to know about torsion modules, torsion submodule and rank and so on as of now. And let me get to the structure theorem. Yeah. So I'll state the structure theorem first. So it will take maybe we won't be able to do the proof today itself, complete proof. We'll see some application of structure theorem, maybe some. We'll see we'll reduce it to a proposition, which is the crux of the matter, and we'll prove that maybe next time. Okay. Now once this stops acting up. I don't know where this MR came from. Okay. Now, okay. So maybe a little smaller. Okay. So what does the structure theorem say? So this is you may have seen structure theorem for abelian groups, and okay, there is some chat. Yeah. Thanks for pointing this out. Yeah. So that's why I couldn't hear any of the responses. Yeah. Can someone speak and I'll check if I can hear? Hello?
Sir, is it audible now?
Yeah. Thanks. Yeah, so were there any questions which I missed? Sorry about this. This is the right time to ask some questions if you have.
Sir, in the homework, there's one question on rank, but there R is not given to be an integral domain.
Yeah.
So,
what question was that?
okay, let me just read it. R is a commutative ring and F is a free R module of finite rank.
Yeah, well, free R module, for free R module, the rank is same as the this length of a basis.
Okay, sir. Sir, and sir, in the previous class, we saw that the rank of an ideal is always 1. So can we say that if M is an R module of rank 1, then it is R module isomorphic to some ideal of R?
No, that's not true. So we saw. So for instance, Q also has rank 1 over Z. Yeah, that also we saw last time. Yeah. So, so in fact, you localize Z, then it will have rank 1. Localize with respect to any multiplicative set not containing 0. Yeah, so the rank will still remain 1. So it's basically the number of linear. So the problem is in Q you can't find linearly independent set of length greater than 1. Yeah, so if you take, for instance, two fraction, 1/2 and 1/3, then they are of course not linearly independent, right? So 3 times, so you can multiply half by 2 and 1/3 by 3 and take their difference, and you get 0. Yeah. So as Z module, these two elements are not linearly independent. Okay.
Okay.
Yeah, and also you can see it in this sense as well, the one mentioned in red, and you can also see it in terms of vector space dimension, because when you invert further, you get Q. Yeah, so you don't get anything more than Q. So it is one-dimensional as Q. Any other question?
Sir, I have one.
Yeah.
If we know that a module is finitely generated and it is torsion free, can we say it is free?
Yeah, so that is not true in general, but it is true for PID. Okay, so so this we will see. Yeah, so this you can see right now the corollary of the structure theorem. But maybe we'll also see an example where this fails. Okay, if R is not a PID.
Okay.
Okay. Any other question?
Yes, sir. Excuse me, sir.
Yeah.
Sir, I had a question. Can we assume that thing which you just said during the first, while answering the first question, that the length of any basis for a free module is same? Can we assume that for a finite? We are assuming finitely generated. Like.
No, you have. I mean, it was to say that if R power n equals R power m, then n equals m. Yeah, that was
yes,
the question.
Yes, sir. The second question in 10.3 of Diamond Code.
Yeah, so you can't assume that. You can assume that two vector spaces have the same. I mean, if the two vector spaces is so for vector spaces you can assume this result, because you have seen that two linearly independent set has the same, two bases has the same length. Yeah, but for modules you can't assume this. Okay. So you'll have to reduce it to vector spaces somehow. Okay.
Thank you, sir.
So yeah, so anyway, so basically there you can replace, if the confusion is about the rank, there you can replace rank by length of a basis. Yeah? The word rank by length of a basis. So what you have to show is that yeah, so basically you have to show this, that if you have a free module, a finitely generated free module, then length of any two bases have to be same. That's another way of phrasing that problem in some sense. Okay. Any other questions? Yeah, you're welcome. Any other questions before we proceed? Okay. Okay, good. Okay, so now let's get to the structure theorem. So as I said, you may have seen structure theorem for finitely generated abelian groups. So you may not have seen the proof, but I hope you have seen the statement. So the statement is this: G be a finitely generated abelian group. So look at this corollary. Then G is isomorphic to some Z power K plus Z mod A1 plus Z mod A2 plus Z mod A. So and direct product of cyclic groups, such that A1 divides A2 divides AM. Yeah? So this is one version, and then there is another version, which maybe I'll talk about it later. Yeah. So the two versions are sort of equivalent. You can recover one version from the other. So, so the structure theorem for finitely generated R modules over a PID, where when R is a PID, is precisely an analog of this. So let M then, so here you have M a finitely generated R module and R a PID, then M you can say is isomorphic to R power K, where K is some non-negative integer plus R mod A1 plus R mod A2 up to R mod AM, where K actually is the rank of M. So here, of course, K could be 0. Yeah? If when M has 0 rank, then also this statement holds. But then, of course, K will be 0. So this factor may not exist. And A1 to AM are elements of R, are non-zero elements of are non-zero and non-units in R, such that A1 divides A2 divides A3 up to and so on up to AM. So, and here, of course, again, M may be, so it may happen that that there no such factor exists. So only it may happen that M is just RK, yeah. Or it may happen that both of them, if M is 0, then of course both the factors are not there and you just get 0, yeah. Okay, so it's possible that K and M could be 0. So is the statement clear of structure theorem? So it's a very important theorem because it leads to it will as we'll see, this is used to prove give a more reasonable proof of canonical form and Jordan form of a matrix, yeah. Existence of rational canonical form and Jordan form. So somehow, so once you know the structure theorem, then it becomes more or less straightforward why this should be true. Okay, so first corollary of this is that say R is a PID, and M is a finitely generated torsion-free R module, then M is a free R module. Yeah, so this of course follows from here. So the proof is this is too thick. Okay. So the proof of this is yeah, so it should be one line proof. So the point is M is finitely generated torsion-free R module. Then the structure theorem tells us that M is going to be isomorphic to R power K plus something like this. But if M is greater or equal 1, so if M is not 0, then of course you can take, for instance, 0 comma 1 bar comma 0, yeah. So this is isomorphic to this, so you can take M such that it maps to this guy in the right hand side, yeah. Then Rm, so which are, yeah, so A1M, yeah. Then A1M is equal to A1 times 0 1 bar 0, which is so 0. A1 bar is going to be 0, yeah, because you have the second component is R mod A1, so A1 bar is 0, so you get 0. So that means you get some torsion elements contradicting. Okay, so I didn't leave much space, but so maybe I'll write here contradicting M is torsion free. Yeah, so I thought I'll just say it verbally. Okay, so make sense? That is just a direct consequence of structure theorem. And of course, and this is also basically a restatement of structure theorem. Just take R to be Z. Yeah. Then any G is going to be a Z module. G is finitely generated Z module. Okay. And apply structure theorem. So this is also a corollary of the structure theorem. Another consequence of maybe these things are, so if R is a PID and M a finitely M a submodule of stop writing like my daughter of a finitely generated free module. So R a PID, M a submodule of a finitely generated free module, then M is free. How does this follow? So point is, so this uses something which we saw maybe last class. So M is a submodule of a finitely generated free module. So M is contained in some Rn. What can we say about Rn?
It is torsion free.
Rn is torsion free. So this implies that M is also torsion free. Yeah. So M, I mean, a submodule of a torsion free module has to be torsion free, right? And M is torsion free, and there's another hypothesis, right? It should be torsion free and M is finitely generated. Why is M finitely generated?
That is Noetherian.
Yeah. So R is a PID, so in particular Noetherian. So once you have a Noetherian ring, in every finitely generated module is Noetherian. Yeah. So this implies so R Noetherian implies Rn is a Noetherian R module, which implies M is Noetherian R module. So submodule of a Noetherian R module is again Noetherian and hence finitely generated. Okay. So write a little below. Hence generated R module. So now you can apply the previous corollary. Okay. So these are some straightaway consequences of this structure theorem. Yeah. So let's see some examples. I mean, so first example is for this guy. So you had someone had asked that whether if M is torsion free, whether it's free or not. Yeah. So this is not true. Even if it is finitely generated torsion free, then it's not true if the ring is not a PID. Yeah. So all the hypotheses are needed. So example. So maybe R you can take it to be ZX or KXY if you like. Or maybe QXY, some field XY. Yeah. So of course it's an integral domain. So so you take a submodule of this. So but it's not a PID. Yeah. So you take a ideal. So for instance 2, x or here x comma y, it doesn't matter which case you are in. So this is your M. So these are, of course, I mean, by looking at it, you can say that is finitely generated. It's generated by 2 comma x here, and this is generated by x comma y. So M is finitely generated, torsion-free because it's a submodule of a torsion-free module. Yeah. So I mean, this is I guess I didn't tell you why submodule of a torsion-free module has to be torsion-free, because I mean, if something is if there is an element which is torsion, then it's in the ambient guy as well it is torsion. Yeah? So that's the so. But is M free? So M is not free. So can you tell me what is the what are the relations, or why it's not free?
Sir,
So the rank of M is 1, yeah, that we know because it's an ideal. So if it is at all free, it has to be singly generated. Yeah. So note rank of M. So maximal linearly independent set, if you like, is going to be rank of M is 1. Yeah. But of course, this is not principal. Yeah. So these ideals are not principal. That's another way of saying it. Yeah. Or you can argue that I mean. These are not principal, so this is one way of saying it, but M is not a principal ideal. That's one way of arguing about it. Other ways, the point is M cannot be generated by one element. Yeah, so this we know that M is not principal, and now you take any two elements in M, then you show that they are linearly dependent. Yeah? So if f comma so I mean, for instance, 2 comma x you can show are linearly dependent, but that way you can show any two elements are linearly dependent. So why are 2 and x linearly dependent? Are not linearly independent, as you just multiply 2 by x times 2 plus sorry, yeah, plus maybe it's okay, minus 2 times x. Yes, this is 0 in M. So so that tells you that 2 and x are not linearly independent. Similarly, you take any two elements and you multiply the second one by the first and first one by the second. They are also elements of the ring, fortunately. So you can do this and say that they are not linearly independent. So it's not principal idea and they are not linearly independent. So you don't have to talk about rank at all. Yeah, so as long as you know that this is not principal ideal, which we have checked, yeah, that this is not a principal ideal. That's how we and that's how we proved that this is not a PID. Okay, any questions? So this gives you an example of a module which is of an R over a ring R, which is very nice. It's a UFD. Yeah, it's very close to being a PID. Just that there's one extra variable added to it. Yeah? is a polynomial ring over a PID. And you have seen that finitely generated torsion-free module need not be free. Okay, so it's a very special property of being free. Is a very special property. Torsion-free is not that special. Yeah, so it's easy to check property. So in that light, this theorem becomes even more amazing. Yeah, so you just have to check whether the module is torsion free or not, and then you can conclude that it's a free module. So it's a very important result. And second is that even over a PID. So so this was one example. Second is R a PID. So we saw that we can't drop the hypothesis R is a PID. We can't even, of course, if the module is torsion, then it has no chance of being free if it is over a PID, right? Free means it has to be of the form R power n. But what if I assume is, so for a module to be a free module over a module over an integral domain, for it to be a free module, it must be at least torsion free. Yeah, because free modules over integral domains are torsion free. But is torsion free enough? So R a PID M torsion free. Does that imply M is free? So I've dropped the assumption that M is finitely generated. Is this true?
No, sir. Over here it would fail because free, as we have seen, it requires a good basis and
Q as a module over Z.
Yeah, so you can take Q as a Z module. Yeah. So we already saw that, or you can just check that Q is not a finitely generated Z module. Yeah. No matter how many finite number of rational numbers you can take, if you take Z linear combinations of it, so you take this smallest positive one, and half of that will not be contained in the Z module generated with. Yeah. So that tells you that this is not finitely generated, but Q is not free. Why? Its rank here. Rank maybe is necessary. So yeah. So you take any set which is bigger than 1. Yeah. So let S contained in Q be a subset such that size of S is greater equal 2, then S is linearly dependent. Yeah. So half or one, like I took half or 1/3, or you take any two rational numbers, then you can multiply by the denominator of the one guy to the other guy, denominator of this one guy and denominator of the other guy, and make some adjustments. Numerator of the so alpha. So you just take R over S and R over S, and P over Q are two rational numbers. Then you take S times P and 2 times R. And take the difference, you get 0. Yeah, I hope. Yeah, both of them are PRs. Yeah, so this tells you that I mean, if at all it has to be free, it has to be isomorphic to Z. But we know Q is not, and Q is not isomorphic to Z as Z modules. Yeah. For that matter, apart from cardinality, there's nothing common between Q and Z. Okay. So these are two examples to keep in mind to say that you need all these hypotheses for structure theorem. Okay. Any questions? Make this smaller. Okay, this has gone a bit too down. I don't know, can you, I don't know if you can read the side panel anymore. Okay. So yeah, maybe I'll hide the example so that you can somewhat read this. Any questions before I get to the main proposition, which will be used to prove this structure theorem? Okay, so so I mean this proposition is essentially the structure theorem, but I mean it's sort of I'll postpone the proof of this maybe to the next class, but I'll say how this proposition implies the structure theorem. Okay, so let R be a PID and F be a free R module of rank I don't know what rank did I choose, rank n, R module of rank n. Let n be a submodule of F, then this proposition says that n is a free R module of rank m less equals n. So it can't have rank more than n. Yeah, it has to be at most n. Moreover, there is a basis. So this moreover part is the important part. Moreover, there is a basis x1 to xn of f of this free module f. And there are elements a1 to am in non-zero elements a1 to am such that a1 divides a2 divides am, and a1 x1 a2 x2 am xm belongs to m, and not only that, the set forms a basis, is a basis of n. Yeah. So they are going to be linearly independent because x1 to xn are linearly independent. So if you multiply x1 by some scalar, a non-zero scalar, and so on, x2 by, they are going to be linearly independent. But what it says is that it's also spans n. Yeah, they belongs to n and they span n. So you can find a1 to am and the basis x1 to xn of f such that these two conditions hold. Okay, so this is the proposition which we will prove. So this proposition will have a longish proof. So I'll start in the next class. So tomorrow, and once we have this proposition, this theorem is essentially immediate from this proposition. Okay. So maybe I'll enlarge it further so that so now what we want to do is use this proposition to prove this structure theorem. Okay. So I mean the proposition is designed to show that the structure theorem is immediate from this thing. Okay. Any questions? Okay. So so let's prove the structure theorem using this proposition. So let M be a finitely generated R module. Yeah. So we want to cook up a free module and a submodule so that we can apply this proposition. Yeah. So how do we cook up a free module? So M is a finitely generated R module. What does that mean? So we have certain number of elements of M which generate capital M. So let M1 to Mn be elements of M such that M equals Rm1 plus Rm. Yeah. So this is a generating set of M. So in such a scenario, you can find a free module of rank n, which will surject onto M. Yeah. This implies. And there exists so phi from F to M, sending EI to MI. Where F is a free module of rank n. So F is Rn, if you like. Yeah, that is how free module of rank n looks like. And EIs are standard basis. Basis vectors. So you can take any basis vectors, but let's just take standard basis vectors. Yeah. And then phi is R epimorphism or R linear surjective map. Yeah. So this okay. R extends to, maybe that's the right, phi extends to. Yeah. So how does phi extends to? Phi of phi of yeah. So maybe I don't want to use A1 to AN, but maybe B1 to BN goes to a summation PIMI. Yeah. Yeah, so this is the map from F to M, and under this map, EI does go to MI, and clearly, so this we have seen, right? So we know phi is R linear, and since MI is generate, and generate M, phi is surjective. Okay, so it's always easy to give a R module homomorphism from a free module to any module. You just declare where the basis will go to. Yeah. So that's why it's easier to give a map from one vector space to another vector space. You just say where the basis will go to. So here's the same principle, where the basis, you decide where the basis vectors will go to, and that determines the R module homomorphism completely. Okay. So you have F of this proposition. What will be the N? So you take N to be kernel of phi. Yeah. So this is contained in F. So N is a submodule of F. So the proposition now tells you that that N is free, but that is not what I care about that much. But the second part is what, yeah. So I mean, it has this, the more refined statement is what I need. Yeah. So now by proposition, there exists a basis x1 to xn of f, and a1 to am. So this will be almost the same a1 to am. There's a slight difference from the structure theorem, such that a1 divides a2 divides am. So this is non-zero elements, and a1 x1. So m is less equal n. M is less equal n. There exists a basis. So m could possibly be 0. Yeah. So if m happens to be free, then of course the kernel n may be 0. Yeah. So, and in that case, you can take so then you can take x1 to xn to be any basis. Yeah, and the second part is vacuously true. a1 x1 a2 x2 am xm is a basis of n. Yeah. So so more explicitly, I can write f to be equal to r x1 plus and this happens to be direct sum r x2 plus r xn. So it's internal direct sum. Yeah, because this is a basis. Yeah, x1 to xn is a basis. So I can write f as this thing, and here n I can write it as so this is a basis of n a1 x1 so and n is contained in this, and then I can write it as r a1 x1 plus r a2 x2 plus r an xn. Yeah, and again this is sort of a direct sum. Yeah. So once I give a basis, I can write elements of f as tuples with respect to this basis also. Yeah, with respect to x1 to xn, and then I can take the quotient. Yeah. So now if I take the quotient, so m of course is isomorphic to f mod n. Yeah, by first isomorphism theorem. Yeah, because we have phi is a surjective map onto m, so m is going to be isomorphic to f mod the kernel of phi, yeah, which is n. But what is f mod n? But f mod n is r x1 direct sum r x2 x1 r xn modulo the submodule r a1 x1. So this submodule is actually contained in the first factor, yeah, and so on. The second submodule in the denominator is contained in the second factor, and so on, up to m, sorry, this was up to m, not till n. So there is an m here. Yeah. R am xn. Yeah, so n has only n factor, so n is a submodule, yeah, so it may not be whole of xn. Yeah, so this tells us that so if you want to take this factorization, then so this we know from how. So this is similar to groups. So so maybe I'll just write the answer first and then do this. So this is Rx1 mod Re1 x1 direct sum Rx2 mod Re2 x2 plus Rxm mod Ram xm plus and then the remaining factors don't have anything in the denominator, so you can think of it as plus 0, 0, 0 here. Yeah, so R m plus 1 plus Rxn. And so here I'll say what I'm using, since so m1 m2 so maybe let me write down the longer version. Mn are modules, and n1 ni contained in mi are submodules. Then m1 direct sum m2 direct sum mn mod n1 direct sum n2 direct sum capital N sub n is. So note that this direct sum is a submodule of the numerator, and this is isomorphic to m1 mod n1 direct sum m2 mod n2 mn mod mn. So as abelian groups, you have seen, I'm sure you have seen this result, right? Yeah. So this is true even for modules. So as R modules also, so the map is going to be R linear is what you have to check. Okay, is this clear? Okay, so assuming this makes sense, yeah. So so this is what I'm using here, and then yeah. So unfortunately we didn't take a break, but maybe we'll stop earlier. Yeah. So so this so of course after the nth factor, you just assume that the submodules nic you have chosen is the zero module, and you get this. Now of course this is isomorphic too. So what Rx1 is basically R, yeah. Rx1 is isomorphic to R, and the submodule RA1x1 is isomorphic to RA1, yeah. Yeah, and its image in this is RA1. Yeah, so this the first factor is R mod A1R, if you like, plus R mod A2R. So A1R, I can write it as the ideal generated by A1. Yeah, so A2 plus R mod AM. And then you get, and this is a free module on m minus n elements, so R power n minus m. Yeah, so I've clubbed these together. This factor I've clubbed here as n minus m. So here what I'm using is that Rx1 is isomorphic to R. So where 1 goes to, let's say, x1, yeah, under this map, yeah, and or x1 or and in the reverse direction, x1 goes to 1, okay, and then ax1 will go to a, yeah, and under this map, R A1 X1 under this map. So let's call it I don't know, alpha. So alpha of A is basically the ideal generated by A1. Yeah. So now you use this, then you get that this quotient is precisely R mod A1. Okay, Rx1 mod R mod A1 X1 is precisely R mod A1. And so on. So same principle to this. Yeah. So we are almost we are almost in the state. Sorry, I shouldn't have minimized it. So we are almost in the statement of it looks almost like structure theorem. The only thing missing is so A1 to AM are non-zero, but A1 to AM could some of these A1 to AM could be non-unit could be units. In the structure theorem, we want A1 to AM to be non-units as well. Yeah? But that is easy to achieve once you have this. Yeah. So so maybe I write it here. Yeah. Okay. So so A1 so A1 of course divides A2 divides AM is given. AIs belongs to R are non-zero. So what we do is just look at so they are non-zero elements. We just look at so some of them may be unit. Yeah. So if AM is a unit, that tells you that all of them must be a unit, because all the other things divide. Anything which divides a unit has to be a unit. Yeah. So maybe let's say some of them are unit. Yeah. So let A1 so let A1 to AR be units are less than equal to M. So if AR is unit, anything before that will also be a unit. So let's say these are units, then what you get is M is so if A1 is a unit, what happens to R mod A1?
So it becomes the zero module.
Yeah, so it becomes the zero module. So the first R factors will go away. Yeah, then M becomes isomorphic to A R mod AR plus 1 direct sum R mod AM. So of course it may happen that R is equal to M, then all these factors go away. And what is this is R is R power n minus M. Yeah. And we get the structure theorem. By replacing M by M minus R. Yeah. M minus R and AI by A R plus I. Okay. So you just renumber this. Yeah. So that and then we wanted to also say that this exponent of the free part is same as rank. Yeah, but that is okay. Yeah. So once we have this, then note finally finally note that rank of M is dimension of S inverse M over S inverse R minus is R minus 0. This implies, S inverse of this right hand side, I'll just put RHS, is precisely S inverse of R power N minus M, because AR plus 1 to AM are non-units, yeah. These are torsion. So this first M factors are here in this case M minus R factors consist of torsion part of M. Yeah. So that will so if you localize that will go away to 0. So remember, as localizing this is same as doing it each factors. So you get only this one. Yeah. So the localizing these things you get 0, and so this implies rank of M is N minus M, which is going to be RK. Yeah. Okay, so the free so N minus M is same as the rank of Okay, any questions? So that completes the proof. Of the structure theorem, assuming the proposition. Yeah, so as I said, the main part of so this is, as you can see, I didn't do anything tricky here. Just realized M as a quotient of a free module, and these are some standard steps. Yeah, so there is nothing tricky. Just writing down the arguments. Okay. So maybe I'll. So I was also thinking of giving you the second version of the structure theorem, but since we didn't take a break, let me stop here. So tomorrow I'll give you a proof of this proposition, and then if time permits, I'll do the second version of the structure theorem. Okay. And then on Tuesday we have a quiz, and next week I'll do rational form and Jordan form using the structure theorem. And that's more or less the syllabus that will complete the syllabus of this semester.
Excuse me, sir.
Yeah.
Could you please clarify the syllabus of the upcoming quiz?
Yeah. So you can. Yeah. So maybe up to the structure theorem. So, but I won't, of course, ask the proof of the structure theorem, but maybe up to the structure theorem.
Okay, sir. Yes, sir. Thank you, sir.
Yeah.
And one more thing about the final examination, the NSEM.
Yeah.
Sir, could you please clarify on the mode and the nature of the examination? Like, we have been provided with a mail in which the dean has suggested some open book structure and other things. Could you please clarify on what would be the exact structure for algebra?
Yeah. So the exam will be similar to what I've been doing for quizzes. Yeah. But you can use books, and as usual, you can't. But you can't communicate among yourselves. Yeah? So so if I see identical question answer scripts, or so unfortunately I did notice in the last quiz some of them. But so you are not allowed to talk among yourself. But you can use the books and all, and it will be sort of similar. I'll upload the question paper at certain point of time, and then you'll get you'll get 15 minutes, and then to see the question paper or download the question paper, and then there won't be any online invigilation, as you may have seen in the email.
Yes, sir.
So that part we don't have to worry about. And but you have to upload everything in the Moodle. Yeah. So even for this next quiz, those who had difficulty uploading things in the Moodle, please practice. So maybe I'll create some dummy quiz so that you can practice uploading some script. And so as long as ISI servers are working, you have to upload it on Moodle. If the servers are down, then there may be some exception, but if the servers are up, you should upload it on Moodle. And that's all. Yeah.
Yes, sir. Thank you, sir.
You're welcome. Any other question?
And one more thing regarding this.
Yeah.
You said we could refer to the books as in the main textbook is 100 foot.
Yeah.
Yeah, but for localization and all, there is material only in the commutative algebra part of Dummett and Foote, like the main details. Only field of fraction is there in the
Yeah.
rings chapter,
Yeah.
but the rest is in the commutative algebra part.
Yeah, or the notes. Yeah. So you have the.
Can we refer to notes? That's what my question is.
Yeah, of course. So you can refer to books and notes, of course. Yeah.
But the theorems would only pertain to the things done in class, as in we can't use extra theorems or results given in the book, as in the universal property of free modules and those.
I did tell you the universal property of free modules verbally. So you can, meaning you giving maps is easy, right? That is what the universal property of free module. So that's a fancy word of saying that defining a map from free module is easy. You just declare where the basis goes. So yeah, most of the results, so you can use the results in the book. That's okay. Or in the notes.
Yes, sir.
Okay. Yeah. Anything else? But whatever result you use, you have to cite it well. Yeah. So this is the result you are using. You have to cite it clearly.
Okay, sir.
So for instance, if you are using some result from the notes, you just say this is the result I'm using. If you are using it from the book, the same principle applies. Yeah. This is the result I'm using, and this is here in the Dummett and Foote. Yeah.
Yes, sir. Yes, sir. Thank you, sir.
You're welcome. Anything else? Okay. So if there are no questions, then maybe I'll stop the